Okay.
So hello, everyone. Welcome to the One World Combinatorics on Words seminar. Our speaker today is Antoine Domenech, and he is going to speak to us about avoiding doubled patterns.
Hello, everyone. So in this presentation, I'll show some results we proved with Pascal. So I'm an intern working under Pascal's supervision, and this will be about the avoidance of double pattern, and it will be divided in two parts. In the first part, we will show some result on double pattern avoidability that we published on arXiv last February, I think. Yes, it was in February. So that's the first part. And in the second part, I will show some idea to go beyond the dichotomy between avoidable and unavoidable. So let's start. Does it work? No, it works. Okay. First, let's all have the same convention. So a pattern is written with letters that we call variables, and we will denote them with capital letters A, B, C, D, and so on. And words will be over an alphabet of letters 0 to k-1. If we have k letters, we take 0 to k-1. And so we are talking about the avoidance of pattern. So let's look what avoiding a pattern means. If you take a look at this example at the example at the middle of the slide, you have the pattern ABA. It's over capital letters, so it's a pattern, and it occurs in the word that's on the right. Because if you take A to be 2-0 and B to be a 1, then you have ABA, which is 0-0-1-0-0 as a factor of the word. That's an occurrence. So formally, an occurrence is defined by a morphism that maps variables to letters. And remark that it's a non-erasing morphism. Each variable must be mapped to at least one letter. We cannot forget a variable. And so it's a morphism, and the image of the pattern must be a factor of the word, just like in the example. And now let's define what's avoidability. We say that a given pattern is k avoidable if there is an infinite word on k letters, so using the letter 0 to k-1, with no occurrence of the pattern. And otherwise, we say that it is not k avoidable or that it is k unavoidable. For example, if you take squares are the pattern AA, then it is known that squares are not avoidable on two letters. The biggest squareless word that you square free word that you can build is of size 3. You can try it. And it's another known result that cubes are avoidable on two letters. And this is proved by the two morphism, which is the morphism that I give below in the slide. You map 0 to 0,1 and 1 to rank 0. You take the infinite fixed point of this morphism, and then you can show that it is cube free. That's a common result. So that's for patterns, words, and avoidability. And now this presentation is about double pattern. So let's define them. A pattern is said to be doubled if every variable occurs at least twice. So for example, the first example I give, A, B, B, C, A, it is not doubled because there is only one C. And so C doesn't occur at least twice. And then the two examples below are doubled. You can look at it if you want. And I insist that it is at least twice. So if a variable occurs 4 or 5 times, it doesn't matter. All that matters is that every variable is at least twice. Now let's go to the results. This work started from a theorem by Pascal in 2016, where in a paper where he has shown that every double pattern is free avoidable, and that is a big result because, as you know, avoidability of patterns in general is a hard problem. So knowing that every double pattern is free avoidable is really a strong result. Pascal has shown in using the power theory method and a bit of studies of some problematic patterns, but a very few number of them. And then, well, we know that they are free avoidable. The logical question is, how many of them are too avoidable? We know that not all of them are too avoidable because squares are not, but clearly they are not all too unavoidable because cubes, are avoidable. So how does double pattern behave? In a previous paper in 2014, Pascal and Alexandre Pinlou had conjectured that there exist only finitely many too unavoidable double patterns. That means that, yes, every pattern is free avoidable, but free avoidability is kind of the exception. The rule of, or what we think is the rule is the true avoidability. Almost, we believe that almost every double patterns are true avoidable, but it's still a conjecture, and it's a hard one. We haven't been able to prove it yet. So we will have to take a look at an easier problem. And for this, we can what Pascal did is improving the result he had shown in 2016 by having one more conclusion on the growth rate of the double patterns. So what is the growth rate? Formally, it's defined as the formula I gave on this slide. So the growth rate on k letters of a pattern P is the limit of the number of words of size n on k letters that avoid the pattern, and you take that to the power 1 to the n. So that's not that might not be very intuitive. So just think about it as what's below, is that the number of words of size n avoiding a pattern is a theta of the growth rate to the 8. So the bigger the growth rate, the more a pattern is avoided. There will be more and more words avoiding it. And so by doing a better analysis of the result of 2016, we've shown that the minimal growth rate of double patterns is square. So that means that the double pattern with the less words avoiding it are squares. But then that's proven using power series theory, and we would like to have a combinatoric proof of this. And so we could have one if we could prove what this conjecture 4 here. So this conjecture 4 is that every square-free double pattern is too avoidable. Obviously, squares are not too avoidable, so a pattern sorry. So the conjecture is that every square-free double pattern is too avoidable, and it doesn't concern squares because squares are not square-free. And so this first of all is something that we believe is true, and second, it will give us a nicer proof of proposition 3. Why? Well, let's do it. So we want to prove proposition 3. First case, if it's not square-free, then P contains a square. Then any word avoiding squares avoids P. So there are at least as many words avoiding P as squares. So the growth rate of P is at least the growth rate of squares. That's the first case. And so for this second case, if P is square-free, then we can apply the conjecture. So it is too avoidable by the conjecture. But if it is too avoidable, then by a classic result, its growth rate on 3 letters it is at least square root of 2. But square root of 2 is 1.4, and we know an approximation of the growth rate of squares, which is 1.3. So the growth rate is bigger than the growth rate of squares. And this, we believe, is a nicer proof, because first, it is a combinatorics runs, and second, it really tells us why the growth rate of squares can be achieved. If you are square free, you are bigger than squares. If you reach the growth rate of squares, it's because you contain a squares and probably nothing else, or not many things else, because you must not forbid a lot else. There will be more work avoiding it. So that gives us a better proof, but it starts from a conjecture, and now what we want to do is to prove this conjecture. It's a bit hard because every square free double pattern is a lot. But what we did is that we studied every square free double patterns with at most 4 variables. And those, they are indeed 2 avoidables. That's the result of the paper we put on archive. And let's sketch the proof. So first, we list all minimal relevant patterns, because square free double patterns, even on at most 4 letters, there are a lot of them. So we have to, as we will be working on each of them, we have to prune the search tree. So if from the avoidability of a pattern we can conclude the avoidability of another pattern, then we will just study the first one. And second, once that we've found all of minimal relevant patterns, then we'll have to show that they are 2 avoidable. So let's go. What are our minimal relevant patterns? Well, first, if a pattern is equal to another up to renaming variables, then they are philosophically the same. It will be exactly the same rule that avoid one and the other. We don't have to study both of them. And we choose to study only the lexicographically minimal one. So if you look at the example below, those 2 are the same pattern. You can see it with the colors. And so we will only study the one on the right because it's lexicographically smaller. That's the first condition. Then another condition will be if a pattern is the reverse on another. The reverse of a pattern is just taking the same pattern but in reverse order. So if you have ABC, the reverse pattern will be CBA. And it has been studied. And a nice property is that a pattern is avoidable if and only if its reverse is avoidable. So we can study only one of them, and we chose to study only the lexicographically smaller. So once again, you can take a look at the example. So the reverse of the first part of the pattern on the top left is the pattern on the top right, which is the same pattern as the pattern below, but renamed. So we will study only the lexicographically smaller. That's our second condition. And then a third condition would be if Q is a pattern and contains another double square free pattern, then we can just take a look at the first one. So for example, those 2 patterns, the first starts with the second one. So we can just study the second one. And now, so that's our minimal relevant patterns, and we can add one more condition, because that still makes quite a number of double patterns. But in the 2016, Pascal had shown that some of the three avoidable patterns are too avoidable. So we already know some patterns to be too avoidable. And while if a pattern contains an occurrence of those known to be too avoidable patterns, we don't have to study it. We know that it will be avoidable. So for example, we already know that ABA-CBC is too avoidable, and it occurs in the pattern on the right. The mapping is the color. So A to I, B to B, and C to CD. As it is avoidable, the run on the right is avoidable. And with that, we have a nice list of minimal relevant patterns. It's still a bit big, but not too big. We can work with it. Now we have to show that they are avoidable. And for this, we have two methods. The first one, and our favorite one, is to use a Cassane's algorithm. So we use Matthew Rosenfeld implementation of it. And what Cassane's algorithm does is, if you give it a small morphism and a pattern, it will test if the corresponding morphic word avoid the pattern. So I gave an example of one of the results it gave us for our paper. So you take F5 to be this morphism and C to be this morphism, this and this, and then a C of F5 to the omega of 0 is a morphic word, and it avoids the given pattern. But this method has an issue, is that this algorithm doesn't work for big morphism, and sometimes we don't find a small morphism that works, so we have to use another method. And for this other method, we will search for a word avoiding the pattern as the image of a de Jong word. That's using the lemma from Pascal in 2004. How does this lemma work? The lemma takes a de Jong word, and then it says that if every small, for some sense of small, image of the word biomorphism respects some condition, then the infinite image will also respect the condition. So here, if every small enough image avoids the pattern, then we know that the infinite image will avoid the pattern. So that's a method that works, but it takes longer. So we prefer to find more morphic words when we can. And an example of what it gives us, if you take W4 be de Jong word over sigma 4, and C to be this morphism, then C of W4 avoid this double pattern. And with those two methods, we have shown that every double pattern on at most 4 letters, square-free double pattern on at most 4 letters is too avoidable. It makes for a big table on the archive paper, but it works. And now let's look back at, sorry, why doesn't it? Yes, let's look back at our two conjectures. The first one was that there exist only finitely many two unavoidable double patterns. And the second one is that every square-free double pattern is too avoidable. A logical question will be, are those two conjectures equivalent? Well, it's not clear. We haven't been able to prove an implication between the two, because there could be infinitely many two unavoidable, but they will not be square-free, and so every square-free double pattern will be two avoidable. And you can and reciprocally, the implication is not clear at all in the other sense. So we don't know if they are equivalent, but we mainly don't know this because we don't have a good way to work with double patterns, with square-free double pattern. We think that we lack a good characterization or a very good property, something to really work with them. Because as I've shown on the previous slide, what we did is study each of the minimal relevant double patterns. That's not a very general method. So they are general methods, but they are not they are not able to prove an implication between these two conjectures. We think that we really lack we lack what we lack is the list of two unavoidable double patterns. That's all, or something that gives us the list, and it would be very nice if we could have it. But then we really believe that those two conjectures are true, and so if they are true, they are logically equivalent. So at least in our hearts, they are equivalent. So that's for the first part of this presentation. So that was what was contained on the paper on arXiv. And now we'll take a closer look at the dichotomy between avoidability and unavoidability. So we already did this a bit, if you recall, here, because we talked of growth rates, and growth rates are a way to distinguish between avoidable formula to compute how much they are avoidable, but there could be another way. A result by Frankel and Simpson in 1995 is that you can build an infinite world that contains only 3 squares. So squares are unavoidable. As I said, the biggest words on 2 letters, the biggest word on 2 letters is of size 3. But you can build a binary infinite world with only 3 squares. And that could give us a way to count how much a pattern is avoidable. It's by counting how many occurrences of a pattern do you need to build an infinite world. Well, that's exactly the idea of what we defined. So we call this the different occurrence number. It's the number of occurrences of a pattern in a binary world. So from now on, we will restrict ourselves to binary world. We already worked a lot on binary world before, but from now on, it's really binary everywhere. And then to count those occurrences, it's important to recall that occurrences are defined by morphism, not by factors. An occurrence is a morphism. So let's see what is important on an example. If you look at the occurrences of A, B, B, A in 0, 0, 0, 0, 0, 0, there is a first morphism, which is the one that's currently highlighted. So A is mapped to 0 and B is mapped to 0, 0. It occurs in the world. There would be a second one, which is this time you map A to 0, 0 and B to 0, 0. And even if it's mapped to the same factors, it's a different morphism. So it counts as another occurrence. And there is, of course, another occurrence. It's A is mapped to 0 and B is mapped to 0. And it occurs at 3 different positions in the world, but it's the same morphism, so it only counts as one occurrence. So really, an occurrence is a morphism. It's important for this notion to be well defined. And on this example, we have 3 different occurrences. Now, what we will do is we will want to minimize this to find how much is a pattern avoidable. And so we'll define the minimal occurrence number. It's the minimal over all worlds, over all infinite worlds of the different occurrence number. That's really not a new notion per se. It's just generalizing what was done on squares to every pattern. And then for this, we have a very nice link with double patterns. because before we worked on double pattern, because avoidability of pattern in general is a very hard problem. So restricting ourselves to double pattern was a good idea. But then, there is a really, really good reason to restrict ourselves to double patterns, is that if you take a pattern that is too unavoidable, then its minimal occurrences number is finite if and only if the pattern is doubled. So you have three cases. One, the minimal occurrences number is 0, the pattern is too avoidable. 2, the minimal occurrences number is a non-zero integer, then the pattern is doubled. And from it's infinite, then the pattern is not doubled. So minimal occurrences number is equivalent, finite minimal occurrences number is equivalent to double pattern. I'll not give all of the details of the proof, but I'll sketch it. So for the direct implication, let's work on an example. We will work by contradiction. So we will take a non-double pattern. For example, here, ABA, CBAB. C is not doubled. And assume by contradiction that there is a world with a non-zero number of occurrences of the pattern. Then you can define the language there is an infinite world. Then you can define the language of infinite binary worlds that have a finite number of occurrences. It is non-empty, and it is factorial by common property of combinatorics of world. But if it's factorial, then it means that there is a recurrent world in it. And then it's lost because the pattern occurs at least once, because it's too unavoidable. So we can take a mapping. A is mapped to X, B to Y, and C to Z. Then as the world is recurrent, the vectors X and Y and XY appears infinitely many times. So what you can do is you fix one XYX, fix it, and then YXY still appears infinitely many times. So it appears as far as you want in the world. So then you map ABA to the first XYX you fixed. Then you map BAB to the YXY that you can take as far right in the world as you want. You map C to what's between those occurrences, and that gives us an infinite number of occurrences of the pattern. But it's a contradiction because our recurrent world is in the language of worlds that have only finite number of occurrences. So it cannot be infinite. It's a contradiction. So that's for the direct implication. So that gives us if the minimal occurrence number is finite, then a pattern is doubled. And for the other sense, for the other direction, it's really technical. But I'll give the idea. Is that if you take a binary world that avoid large repetition and is of some avoid large repetition and is of some fixed exponent, such binary world exists by a result of Roomian stuff. Then you can show that this world this world cannot have infinitely many occurrences of a double patterns. It's really the same idea as what you can do with squares, because if you take a world that avoid large repetition for a good exponent, then it cannot have infinitely many squares, because that will give a very large repetition of bigger than the exponent. So if you take the good world that avoids repetition, it works, and that's why we will be studying only double patterns for this notion. Our work on it is not finished, so from now on we have only conjectural minimal occurrences number. We conjecture those on looking at large binary world, so we really confident that that those conjectures are true. It's just that we did not have the time to find the morphism or the image of a de Jong world that works. And another remark is that the minimal occurrence number is a minimum. So that means that the number in this table are a lower bound on the minimal occurrence number. Because if we can't do, for example, a large binary world with 2 squares, then we can do an infinite binary world with 2 squares. So those in the table are indeed lower bounds. So let's take a look at them. First, there is squares. Well, squares, it's well known that we can use only 3 squares. Then we can see that there are a lot of double patterns on 3 variables that need only 1 occurrences. So yes, they are 2 unavoidable, but we can build a very large world with only 1 occurrences, so they are not that much unavoidable. And what's interesting is that for some of them, it goes up. In particular, for ABBA, it goes up to 8, which is kind of a lot compared to the one that are 1. And for ABBA, we also have another result. It's that if you take this morphic world, so you take F5 to be this morphism, C to be this morphism, and then C of F5 to the omega of 0 is a morphic world. It's a morphic world that has only 8 occurrences of ABBA. So for ABBA, it's not a conjecture. We know that 8 is a lower bound, and that it is reached by this morphism. So it is the minimal occurrences number. And a very interesting property is that there is only 1 language of factors for the worlds that are avoiding, for the worlds with only 8 occurrences of ABBA. So if you take any infinite world that has only 8 occurrences of ABBA, then it will have the same language of factors as this one. So ABBA, not only is it hard to avoid because we need 8 occurrences, which is the maximum we have for now, but moreover, they are philosophically only one way to reach A. It's by using this world or any other world that has, or another world, but this other world that will have the same language of factor. So we can say that it's the same. And then we could also compare ABBA to A, BC, BCA. So ABBA needs 8 occurrences, and A, BC, BCA only needs 1. But A, BC, BCA, when we parenthesize this as this, we can see that it's an occurrence of ABBA. So just by forcing one variable to become 2, which is to mean that by adding the condition that on ABBA that the image of B must be at least of size 2, then the minimal occurrences number goes from 8 to 1. So from the maximum to the minimum. Why is this? Well, first reason is that if you force the image of B to be at least of size 2, then you forbid all basic occurrences. And also, that remove occurrences. And also, as the image of B must be at least of size 2 which is mean that we are looking at A, BC, BCA. Then it allows other occurrences. We could take occurrences of A, BBA, where the image of B is of size 1. The image of A is very big, and we can use a lot of occurrences of those. It will not matter for A, BC, BCA, because the image of B is 1, so it cannot be a BC. because we are using non-erasing morphism. So really, ABBA is an interesting one. And one final thing we can say is that the only occurrences that's needed for A, BC, BCA is an occurrences that we use for ABBA. And remember that there is only one language of factors that which is minimal occurrence number 8. So it's in some sense it's a required occurrences of ABBA, and just using it is enough to build a large rank for A, B, C, BCA. So that's what I had to say about ABBA, and that's more or less what we did on this on this notion. So what we could do next is find infinite world for those patterns, or look at the growth rate of the language that are avoiding them. So there is still work to do. I don't think that it's really hard. It's just that we didn't have the time, and it would I think it would make for a nice part in a paper. And well, that's all I had to say. So do you have any question?
Oh, thank you very much, Antoine. Yes, does anyone have any questions? You mentioned one result quite early about doubled. If a doubled pattern is too avoidable, it has growth rate at least square root 2.
Yeah. Come on. Yeah. Yes.
Where does that result come from?
It is proven in our paper with Pascal that we published on February on Archive, and in this paper is proven by taking a closer look at the power theory method from 2016. So it works. So this result is true. The minimal growth rate on 3 letters of double patterns is this curve. But the starting point of our work, of the work I presented here, is that we would like to have a combinatoric proof, and this conjecture will give us a very nice combinatoric proof.
Okay, great. Does anyone else have a question? All right. If not, thank you so much, Antoine.